Hello everybody, welcome to section 4.5, and we're talking about exponential and logarithmic equations. And we're going to take advantage of some of the properties and things that we've learned about exponents and logs to solve exponential equations that contain common bases, solve exponential equations that do not contain common bases, solve certain kinds of logarithmic equations, and deal with application problems that involve exponential and logarithmic equations, especially in the next section, 4.6. So in this section, we're going to look at exponential equations which contain common bases. And there are really three kinds of exponent equations that we deal with overall. One of them, of course, is this form. I consider this sort of the easiest form, a to the u equals a to the v. A to the u equals some number b, or a to the u equals b. This particular example that I'm dealing with here below is actually an example of this first one. That is, logarithms that contain the same bases. So what does that mean for us? If we take 2 to the 2x equals 32, this is actually an example of this kind of problem because, well, what do we say? But that 32 is a power of x, right, of 2, right? It's 2 to the 5th power, right? 2 times 2 times 2 times 2 times 2 is 32. So what do we say? Well, that means then that 2x must equal 5. If it is the case that a to the u is equal to a to the v, because exponential functions are one-to-one, then it must be the case that if we have that situation, we have a really easy case where, well, u must equal v. So 2 times x equals 5 indicates that x equals 5 halves is our solution to this equation. So let's try another one. Let's try one that's kind of similar. It says this actually still falls under the rubric of certain kinds of equations, exponential equations, which are actually relatively easy to solve if we know what to look for. Right? So what could we do right here? In this case, let's see what happens. How could we solve for x? This is actually sort of a weird one right here, but we're calling it type number 1. It's really type number 2. What does this mean? Well, this is the kind of equation where we have to isolate this. So one of the tricks that you have to know is that whenever you have an exponential type of equation, the very first job is to isolate the exponential part. And more specifically, in this case, we'd have to isolate e to the x as our very first step. So before we start trying to do anything to solve for x, we need to isolate e to the x first. So what does that mean? In this case, we would have to add 2 to both sides. So we're going to get 5 times e to the x equals 53 plus 2, that's 55. But we're not done isolating, right? We have to divide by 5 on both sides. So in fact, e to the x is equal to 55 divided by 5, that's 11. Okay, so now that we've got this form, what do we do with it? Well, the trick that we use in this case, right, because this is type number 2 right here, we would want to think to ourselves, type number 2 right here, we want to think to ourselves, well, how do we get x by itself? And the key is that we use our definition, right? And by definition of the natural logarithm, we would say that if we have e to the x equals y, it is only because, if and only if, there's my abbreviation, if and only if, x is equal to the natural log of y. So in other words, because we have a definition of some base raised to an unknown power equals y, we would try to find x by taking the natural log of that. Now, another way of thinking about this type of problem is that we could say that we could use a particular rule right here about logarithms, and it goes like this. if we have a logarithm or a natural logarithm of some number a, and say that it is equal to the natural logarithm of some number b, what must be true? Well, it will be because a is equal to b. Because a natural logarithm, like an exponent, is a one-to-one function, that must be the case. So one thing we could do right here is say, well, let's take the natural log of both sides equally. So the natural log of e to the x equals the natural logarithm of 11. And in this first case, because natural log and e to the x are inverse functions of one another, right? Remember, again, we're thinking over here that we're taking the logarithm base e of e to the x, and we had a rule that said that that just undoes itself because the base of the exponent and the base of the logarithm match. We just get x on the left-hand side. So x is equal to the natural logarithm of 11. Now, for our purposes, if we're taking a test or something else, that's it. There's nothing else I can do with this term because I haven't got a calculator to evaluate it. If I did, I could call up my calculator and I could just tap in 11, take the natural log of that, and I'd get 2.398 or so if I rounded to the nearest thousands. But in this case, we're going to leave it in this form, and we're going to call it exact form. Why do we call it exact form? Well, it's exact form because if we put the number into our calculator, the best that we can do is get this big long string of numbers, which is nothing more than an approximation of its actual value. The natural log, since the base e is an irrational number, gives us an irrational value for x. So writing it as x equals the natural log of 11 is considered more exact, and that's the way we'll leave it. As a general rule, if you're solving these kind of exponential equations, leave it in exact form. An exact form would be the form that you would write when the very next step after it would be to use your calculator. Okay, more to come in the next